familiar with how we measure blood pressure. We have systolic pressure and diastolic pressure. Systole is contraction of a particular chamber of the heart. All four chambers of your heart in one heartbeat go through a period of systole where they are contracted. We call when the heart or the chambers of the heart are not contracting diastole. That's relaxation in those areas. Okay. So in one heartbeat or one, what we call a cardiac cycle, every chamber has systole, diastole, systole, diastole. So contract, relax, contract, relax. We offset, okay, the systole and diastole at the atria and the ventricles. So when the atria are in systole, the ventricles are in diastole, and vice versa. Okay, so that's what's going to be there. At rest, this is really important, guys. At rest, we spend about 60% of a cardiac cycle. Okay, 60% in diastole. So in any given, like 1 second period of time, 60% of that time in your heart rate is spent with the heart relaxed. This is going to become really, really important for changes in things that happen during exercise. Diastole is wildly important to allow blood to get into each chamber of the heart. It allows time for that chamber to fill up with blood. Okay. And so because of that, it's really important for determining stroke volume and cardiac output. All right. So if we spend 60% of our time there at rest, when your heart rate is around 70 beats per minute or thereabouts, as heart rate increases, the total amount of time between it takes for each heartbeat, between each heartbeat, shrinks. And as it shrinks, the amount of time spent in diastole is going to shrink as well. And at some point, that's going to be a problem for us. And we'll talk through what that looks like as we go along. But I want you all to know those numbers and why it's so important. Okay. All right. That's systole, that's diastole, that's that contraction pattern that we have in the cardiac muscle. Okay. Now, most of you have seen an EKG, right? Or an ECG. I don't know why we call it an EKG. There's no K in those words. Okay. But you've seen an EKG. I'm not going to make you interpret an EKG. All right. In some of our other classes, we do. I'm not going to show you guys, right, atrial fib and say, can you tell me what's going on or anything else? But I do want you to be able to see an EKG and understand the kind of three primary waves or parts of an EKG that we need to see. Just a normal, healthy sinus rhythm is all I want you all to know. Okay? To get an EKG, we put electrodes around your heart here. And those electrodes measure the electrical activity of SA node, AV node, right down. It measures the transmission of action potentials in the heart that are going to initiate the contraction and relaxation of the atria and the ventricle. Okay. So we have a P wave, the QRS complex, and the T wave that are the three things that I want you to be able to identify and understand. And so here's a normal EKG showing two cardiac cycles. Okay. One here and one there. Technically, if you were reading an EKG, we would say you're supposed to measure from R wave to R wave. So it's really only one cardiac cycle. But for our purposes, we're gonna say that it's two. Okay. What you have here with normal SA node driven rhythm is a P wave, which is going to denote depolarization of the atria. There's a normal SA node firing. The atria are going to get an action potential. They're going to depolarize and go into systole. That is going to be picked up. That's what this P wave is. Okay. Then we get QRS, which is our denoting that there is ventricular depolarization. We've gone down the septum, down the bundle of His, through the Purkinje fibers, across the ventricles. The ventricles are depolarizing. They're now in the systole. Okay, so atria fire, ventricles fire. Then there's this T wave at the end that is going to denote basically the repolarizing, the restoration of those ionic gradients and current resting membrane potential there. That's going to show ventricular repolarization. The atria also repolarize, but it's hidden. It happens while the ventricles are contracting. So atrial repolarization is hidden under the QRS. Okay. That's all I want you to know. P wave, QRS, T wave. P wave is atrial depolarization. QRS is ventricular depolarization. Okay. T wave is ventricular repolarization. That's it. Okay. Can we do that? That seems okay. Now, if I put one of these on all of you, there is this one little segment here from the end of the QRS to the T wave. And if we see changes here, that's one of the most surefire ways to diagnose that somebody is experiencing ischemia in their cardiac muscle. They're basically having or about to have a heart attack. It's a thing called S to T segment depression. This line, rather than going up quickly like this, looks kind of slanted, like so. It's called S to T depression. And that is that somebody's having a heart attack. Okay. So the big use of an EKG is to identify the electrical signals and if they're conducting electricity in the cardiac muscle correctly. Okay. It's a diagnostic tool to understand those things. When you do an EKG, if any of you all are in exercise testing and prescription, or if you're going to take it, you guys will be shown how to do what's called a 12-lead EKG. We put electrodes all around here, 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 all around. And depending upon which collection of leads you look at, it lets us see things that are in the right atria, the left atria, the right ventricle, the left ventricle, okay? By looking at the signal in different ones, we can not only see, is there a problem, but we can more closely pinpoint where in the heart is there a problem. And that is why it's such a powerful diagnostic tool. You think you're having a heart attack, you go to the hospital, they're going to put EKG leads on, they're going to put you on a treadmill, they're going to try to make you have another heart attack so they can figure out where the problem is. Okay. Like immediately. That's what they're going to do. So it's kind of a crazy backwards. Okay. Sorry, you had a question?
Yeah, for both the ST and the T section, it says that they're labeled ventricular repolarization. Is it like one ventricle, then is it just like a difference in repolarization speed?
There is going to be, so part of it is going to be the distance of the particular ventricle from the electrons. And so you're going to see whichever one you're closest to is going to be the one you're going to pick up first. And there's going to be a little bit of a delay to the one that's farther away.
Just an observable delay. Okay.
Yeah. Okay. So that's our EKG. All right, that shows those things. You want how to put this on a worksheet? You want this to be your test? No? Have y'all seen this? Do y'all do this in anatomy or in human physiology? So what this is we've mapped out, here's the EKG, right, in red down here. It's showing pressure. So this is blood pressure response. And then we're marking it's all the way across one cardiac cycle or several cardiac cycles. But we're showing then when the aorta opens, when the atrioventricular valve closes, it shows pressure, it shows movement of blood and all of those things. And then it's showing the volume in the left ventricle. Volume comes up, volume goes down because we're getting an injection. It rises back up again. So it's trying to overlay the physical events in the left ventricle with the electrical events and the pressure events that are driving all of those things together. Okay. This is just if this is a thing visually that helps you guys. You don't have to know it. We're not going to make you all memorize it. or anything else, but I know that some of you all are much more visual learners than others. And so this is a thing that might be a way for you to try to tie together cardiac conduction, blood pressure, the actual physical events in the heart, when blood gets ejected, when blood fills back up during diastole, et cetera, et cetera. Okay, so that's what this is trying to denote. Okay. Okay. All right. Everybody who has a drink in front of you, okay, do this with me. Okay, we're gonna take a little bit of a drink. Cheers. Okay. All right. You drank a little bit. Is there stuff still left in your cup? Okay. So, what you guys just took out, okay, what we just took out is going to be our example equivalent to a cardiac variable that we call stroke volume. Okay, stroke volume. What stroke volume denotes is every time the left ventricle contracts, a certain volume or amount of blood gets ejected into the aorta and leaves the left ventricle. Okay, that amount is termed stroke volume. It is the mathematical difference between what we call end diastolic volume and end systolic volume. This is a thing that I think we overly complicated. End diastolic volume is if we imagine that I have a 12-ounce can here, okay, and I'm running water out of a faucet into my can. That diastolic volume, diastole, right? The left ventricle is relaxed. I run the water in and I fill my can up. Okay. I got 12 ounces in there. That is end diastolic volume if this was my left ventricle. So it's the same thing. We're filling during diastole, fills up. That's end diastolic volume is 12. Okay. In systolic volume is, and I'm not going to do this, but I could, I suppose. I squeeze the can, right, which raises the pressure and forces the fluid out. Okay. So I have a full can. I take a drink. I pulled some fluid out. Now what's left in here is in systolic volume. Okay. At the end of cardiac contraction, in a lot of instances, especially at rest, there's still blood left in your left ventricle after your heart beats. Okay. So the amount that I drank is my stroke volume. Does that example make sense to you guys? Do y'all sort of understand? So while the left ventricle is relaxed, it fills up with blood. That's in diastolic volume. Then it contracts and some portion of that blood leaves. What's left in there is called in systolic volume. You subtract those two from each other and you can figure out how much got ejected into the aorta. Okay.
I understand. Is there a physiological reason like why you have blood left? Like why doesn't it just use all the blood out?
It's going to become important during exercise because we don't need to max out stroke volume at rest under most instances. But it can be beneficial to us to raise our stroke volume like during exercise or something else. So my guess is what all of it does is it functions, it gives us a reserve. So we're not operating at our maximum capacity all the time. That's a guess, but I don't know. That's a good evolution question. Something else. Okay. If we take stroke volume and we divide it by end diastolic volume, we get a parameter that is not that useful to us during exercise, but it's actually very useful in cardiology. It's called ejection fraction. So ejection fraction is mathematically what percentage of end diastolic volume is your stroke volume. So basically how much blood gets ejected out every time the heart beats. Most of you guys at rest have an ejection fraction of about 2/3. Okay, so you've got about a third of your end diastolic volume that's gonna stay in there that we can eventually eject out if we can make our cardiac contraction harder. Okay. If you have a person that has high blood pressure, okay, aortic pressure is higher, you have to squeeze harder to get the blood to go out, their ejection fraction will fall. People that have worse cardiac function have a reduced ejection fraction. Okay, so one of the things that we got to see, my father-in-law, who will be here today for trick or treating, my father-in-law had a heart attack about 6 weeks ago. And one of the things that we got from all of his stuff was they did the EKG, did all the stuff is they put the ultrasound on and they were measuring. We know what his ejection fraction was before and after they put a stent in. Okay. And he was down at about 40% ejection fraction at rest. Pretty low. Okay. It's not super duper low, but it can be low. All right. And so this is one of the things that I want you guys, it's not that useful to us for understanding exercise, right? Because you guys are young, you're otherwise healthy, you've got normal responses here. But this is a thing that if you have a parent, a grandparent, right, and someday maybe you, right, to understand that's what this variable means. That's why it's important. This is what it's telling us about those kinds of things. And if you guys that work in a hospital, you work in a PT clinic and somebody comes and they may have all of these numbers for you and you can look at them and have a conversation with them about like what's going on there. Okay. That's why ejection fraction is important. Okay. So that's stroke volume. We've talked about, although we haven't really called it that, we've talked about heart rate. Heart rate is, right, cardiac conduction system, beat, 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 beat. We calculate heart rate as the number of beats per minute. Any of you that have a watch that tracks your heart rate, look at what your heart rate is right now. Got to where am I? Look at what it is right now. Okay. Who wants to share?
77.
Okay, Jose's is 77. Okay. Hey, what's yours? 94. See, I made it go up with me. I call on you, it immediately goes up, right?
It was.
Hormonal response. Epinephrine, norepinephrine. What a drug. Okay.
It was 76 2 minutes ago.
See, it was 76 2 minutes ago. There we go. Okay. So you have a heart rate that is the number of times your heart beats in a minute. You have a stroke volume that is every time it beats, here's how much blood gets pushed from the left ventricle into the aorta. If we multiply those two numbers together, okay, we get a functional parameter called cardiac output. Cardiac output is a volume of blood that leaves the left ventricle and enters the aorta in 1 minute. Okay, in 1 minute. So we abbreviate cardiac output because of Latin or Greek or some shit as Q. Okay, so cardiac output is equal to heart rate multiplied by stroke volume. So it's beats per minute multiplied by milliliters per beat. We do a little math, a little algebra. We cancel out some units and we get milliliters per minute, but it's usually high enough that we then express it as liters per minute. Liters of blood that come from the left ventricle into the aorta in 1 minute. Okay. At rest, most of you guys are going to be somewhere between maybe 4 and 6 liters of blood per minute get moved from the left ventricle into your aorta. Okay. Weirdly enough, most of you have a total blood volume of about 4 to 6 liters blood in your body. So a rough estimate, it's not always true in everybody, but a rough estimate is you move all of the blood in your body through the heart into the aorta 1 time every minute. Okay. 1 time every minute. So it's 5 to 6 liters per minute there. As we exercise, we make stroke volume go up, we make heart rate go up, right? We make Daya's heart rate go up from just by doing all of that, then cardiac output goes up. If it beats faster, then there's more that's going to go. Okay. So most of you all can raise your cardiac output about 4 to 5 times. Okay, what it is at rest. So an average person, maybe somewhere between 18 and about 24 or 25 liters of blood per minute of cardiac output during high intensity exercise. People that are super trained have really, really large blood volumes, have very, very large left ventricles. They may be able to get up into the low to mid 30s in cardiac output. Cardiac output, okay? Max cardiac output is strongly predictive of max VO2. Okay, of max VO2. As oxygen consumption and energy use goes up, cardiac output goes up in a very linear manner that almost exactly matches it. Okay, right? We're using oxygen in our muscles. We need to circulate more blood that has more oxygen to be able to let it extract. Okay, so whoever has the biggest cardiac output wins the race. Okay, so here's my question. How many of you are between 19 and 22 years old? Almost every one of you, okay? You guys all have an age predicted max heart rate within about 3 beats per minute of each other. Okay? We're just gonna say all of y'all are right around 200 beats per minute of max heart rate. If max cardiac output is max stroke volume multiplied by max heart rate, if the assumption is that every one of you, except for a couple in here, me and my midlife crisis, cannot, right, you all can get your heart rate to the same place. So then who has biggest cardiac output? What page? Whoever has the highest stroke volume. Who will have the highest stroke volume?
Cardio bros.
I'm sorry?
Cardio bros.
What is a cardio burn? Do you mean like a cross country runner?
Yeah.
You are correct, but why? Why is their max stroke volume bigger? Fernando?
When you run or work out or something, you get more plasma, and so then you have more blood,
Mhm.
and so then you have higher and diastolic, and so then you have a higher stroke.
Okay, you're half correct. That's half of the answer. That's very, very good. They do have larger blood volumes, larger plasma volumes. That leads to greater filling, higher end diastolic volume. But then there's another thing.
The left ventricle is bigger.
Yes.
So it can contract harder.
Yes, they literally have a bigger heart. Okay, left ventricle is bigger. So rather than having 12 ounce, okay, I've got a 16-ounce can, or I have beer's half gallon. Okay, be able to do those kinds of things. That's the answer. And we'll talk about where these adaptations come from and why. But that's why cardiac output is so important. Okay, that's why it's so important. Okay, now I'm going to walk us through factors that affect cardiac output. So we're going to talk about heart rate, then we're going to talk about the things that contribute to stroke volume, okay, and how those things can change at rest and during a bout of exercise. So we're going to start with heart rate, okay? We're going to start with how we regulate heart rate. At rest, most of you have a heart rate when I'm not calling on you of about 60 to 80 beats per minute. Some of you that are more highly trained, or maybe you had a pharmacological intervention this morning, it might be higher or it might be lower, okay? I took my beta blocker this morning. It will be interesting to know if mine was a little bit lower on all of that. Very highly trained endurance runners, maybe in the 30s. My dad, when he would track his when he was a little bit better trained, was in the high 20s on those kinds of things. Okay. And then if you're very sedentary and stressed, it may be 100 beats per minute, thereabouts. Okay. Dan?
Yeah, like you're highly trained, or how can it get as low as high 20?
How can it get so low? Your stroke volume goes way, way up. Okay. As you get cardiac hypertrophy, as you get blood volume expansion, if the assumption is you have the same body size, the same muscle mass, the same sort of resting metabolic demands, if stroke volume goes up, to make cardiac output equal, heart rate can go down. Right? So if you still need 5 liters per minute of cardiac output, if your stroke volume goes from 80 mLs to 120 mLs, then heart rate can dip and still make that equation balance out. Does that make sense? And that's the primary reason that it goes down. Partially through that, it also goes down a little bit because of exercise reduces stress. It reduces the influence of epinephrine and norepinephrine, increases vagal tone. You get a little more acetylcholine, and so it will dip it that way too. Is it safe? Yes, it's actually healthier to go that low.
Do you want to specify between positive and negative hypertrophy of the left ventricle?
We will get there.
Okay.
That's, I think, later on. We'll talk about there. You can have bad hypertrophy, hypertrophic cardiomyopathy. We'll do Fernanda.
Okay, so yesterday I was trying to get out, right, and there was like this older man,
Yep,
like.
me. I got
I
it.
don't know, it's like actually probably like, I don't know, early 70s.
Okay.
He was older.
Just gonna say he's older. He was in his 40s.
He had a really low heart rate of like 40.
Yeah.
Something, and I walked into the room thinking he's fit as fuck, you know? He's like. I was like,
A very reasonable assumption if that's your heart. They have him dosed up on beta blockers. Do you know? What's he on? You can give a drug that artificially lowers your heart rate.
no, yeah, actually, like his heart rate was just low, like that was the whole.
Okay.
Physical therapy.
Okay. Okay.
Yeah, he said he used to run marathons, so to him it was always fun until it wasn't. Then like at what point is it like not? You know what I mean, like, what? Like, is there like an age where it's just like, you're actually not fit, you're just like not feeding enough for your body to receive stuff? You know what I mean?
That's an incredibly difficult question to try to answer. I don't know. I mean, you're fine until you're not. I mean, that's the story of human existence, right? You're fine until you're not fine. Everything is okay until it's not.
I was in chiropractor like a long time ago when I was in high school, and he said my heart rate was really low because I was sitting there and they took my heart rate, and then he was like, "Do you drink caffeine?" And I was like, "Yeah," and he was like, "Well, your heart rate's," and he was like, "Have you drank it today?" I was like, "No." He's like, "Well, your heart rate's really low because you haven't drank caffeine today. You need to stop drinking caffeine." I was like, "Okay." But
So caffeine's a funny drug. Caffeine mimics the effects of epinephrine and norepinephrine, and it will raise your heart rate, but it mostly only does so when you're exercising. At rest, it has very minimal effects. There are some studies where they see at rest that a high dose of caffeine actually lowers your heart rate and everything. So
he was
no.
saying that like it gets so high, and so when you jump drink it, it gets really low. Like that is why it's so.
No, it was just low because it was low because it was probably because you were relatively fit and those kinds of things, so. Good questions. Okay. When we exercise, your heart rate increases and it increases in direct proportion to exercise intensity, to the metabolic response, okay? All of you all that have a watch or a tracker of some sort, right? It uses your heart rate to predict your energy expenditure during exercise. You have to put in your height and your weight in there and your age, and it uses that to estimate everything. We use heart rate, those of you again that have had testing and prescription, we can use heart rate or specifically heart rate reserve. We can calculate a target heart rate during exercise, and we can guesstimate your percentage of VO2 during exercise based on what your heart rate is. Okay. It is the way to prescribe exercise. So that's what all the trackers are doing and monitoring those particular ways. Heart rate is interesting. You guys remember when Ty taught you, I'm sure that you do, that when we start exercising, VO2 goes up, but there's a bit of a lag. It takes it a couple of minutes, right? We call that oxygen deficit, right? Heart rate has very little deficit. I'm here, I start doing jumping jacks. Within about 10 seconds, it's up and it's steady and it's ready to go. Whereas my VO2 might take 90 seconds or 2 minutes to lag and get caught up. Heart rate goes up and we'll reach steady state very, very, very quickly. Okay. We can calculate your what's called age predicted max heart rate by taking 220 and subtracting your age. Or if you don't like that equation, you want a more complicated one, you can take 206.9 minus 2/3 of your age. And you get basically the same number within like 1 beat per minute. Because somebody thought it was better to try to have a more complicated equation. Okay. So with training, age is the big thing that predicts your max heart rate. Doesn't matter how highly trained you are. You can't make your max heart rate go up. You can't increase your cardiac output by increasing your max heart rate. Okay. Now, maybe if you take some caffeine, I have seen people in our studies on caffeine doing maximal exercise with heart rates of like 209, 210 on those things, which freaks people out when they see their heart rate's that high. Like, is my heart going to explode? They were fine. All those things. But it's very, very stable with training. When you get to be not my age, but a little bit older, then if you're highly trained, you may preserve a little bit of your age predicted max heart rate. My dad gets pissed every time I talk to him. Because when he gets on, when he goes to the physical therapy and he rides the bike and things, that he can't get his heart rate up as high as he thinks that it needs to. And I'm like, Dad, you're almost 80 years old. Like your age predicted max heart rate is like 140. And you know, you're at 125. I'm like, you're at 90% of your age predicted max heart rate. Like you're working hard. It's like, yeah, but I used to be able to get it to like 180. I'm like, you're not getting to 180 anymore. Like it's just not how it goes. So there are some things that there was a question that
So how high is too high for heart rate? Is there such thing as too high?
probably there's a thing that's too high. So the big issue that happens as heart rate gets really, really high is stroke volume, because diastole gets so short, is that stroke volume can begin to fall a little. And the bigger thing is the only way to get it that high is you're trying to do some kind of exercise and you'll get there and you can't continue. So then you stop and it comes back down. I mean, it's hard to get it high enough under, like I can stretch you out and make it go up, but it's going to be hard to get it anywhere near what you would get during max exercise. So in that way, it's not particularly dangerous like that person. That makes sense. Okay. Happy Friday, happy Halloween, right? Have a good weekend. Make good choices. Okay, we'll see you guys on Monday.
We have dinner too.